All right. Again, theorem 416 is designed to take these functions, and depending on whether they're even or odd functions specifically, you can simplify the process quite a bit by determining how the function interacts around the origin. So let's take a look. This theorem has two parts, and in this case, we're going to assume that f is going to be integratable, meaning it's first of all has to be possible to do this in the first place, and it's on the interval between a and negative a. So we have some symmetry here. This is an important piece in order to consider the fact that this function is going to be an even or odd function. It has to be centered around the origin. Now, if it is an even function, or an odd function, there are two simple ways to simplify. One simplifies just one of the steps. The other simplifies almost entirely. So let's take a look. If it's an even function, which means that it is centered and reflected across the y-axis, the integral from negative a to positive a of f of x dx is equal to the integral from 0 to a times 2 of f of x dx. Because it is symmetric on the y-axis, this idea is actually pretty easy to explain when we look at a picture. So let's look at an even function. So remember from algebra, even functions are defined as those being situated around the y-axis, symmetric to it. So I'll use a standard function like cosine. Cosine is even, meaning that to the left and to the right it does the same basic thing. If we assume that my a and my negative a are right there and right there, what it's saying is this area in that spot is equivalent to this area times 2. Which makes a lot of sense, right? It's even, so it's symmetric. So left and right hand side have to be the same. So again, it makes sense that these two areas can be simplified to a smaller version of the same problem. And as we've seen in the past, ones that have a 0 in it typically simplify a lot easier. When we plug them in, most of the terms tend to disappear. It's much better if it's an even function for it to do this. So again, if we are looking at an even function, this gives us a very simple way to at least mitigate some of the damage of doing this function. And instead of looking at the larger problem from negative a to positive a, I can look at the smaller problem twice between 0 and a. For odd functions, it's even nicer. Because the function is odd, as a reminder, functions that are odd are those that are reflective across the origin. So the integral from negative a to positive a of f of x dx, assuming it is odd, will always be 0. And again, from a picture standpoint, that makes a lot of sense. For this example, I'll use another trig function, sine, which is also considered to be an odd function. As a reminder, the sine function starts here, comes up, comes back down, and this side does the exact opposite. And so it's pretty easy to see that, again, if I choose a negative a and a positive a, the amount that is below is going to match the amount that is above, and therefore will cause them to cancel, leaving us with an area total of 0. Because again, remember, it's about the relative area based upon the axis. So if the same amount is above as is below, the area will be 0. There are not a lot of problems that deal with this function, and you don't have to memorize these rules, because obviously you could just integrate and see if this will happen. But for some functions, it is much nicer to do it with these rules because of either getting them to go to 0 on the bottom, that makes it a little easier to do, or just making it really simple to be like, oh, it's 0, it's odd, done. So again, if it matches a specific form, it allows us to take these functions and find their values a little faster, a little easier. But again, these are optional pieces. Great if you want to use them. If not, you're just going to end up doing more work. Let's look at a couple examples where we could use this process. I'll do it once where I use it without the theorem, and then once again where I do it with. The with will obviously be much faster. Let's take a look. In this case, here's my function. we're doing the integral from negative pi over 2 to positive pi over 2 of, sine cubed of x times cosine of x plus sine of x cosine of x dx. Okay. Proving this function is odd is simply a matter of testing how the pieces fit together with a negative. It turns out this function is odd. It's one of those consequences. Remember, to prove something is odd or even, it's a very simple test. If it is even, what will happen is f of negative x will be the same as f of just regular x. Meaning if I plug a negative into the function, nothing changes. If it is odd, the opposite happens. Odd functions have the unique property that if I plug a negative into the function, a negative pops out of the function. Meaning the entire thing switches signs. Everything that was positive becomes negative. Everything that was negative becomes positive. If you do it to this problem, it is an odd function. The reason being, sine is odd, so when I plug a negative in here, it'll have a negative pop out. Cosine is even, so it'll actually disappear. A negative times a positive would make this a negative function. Plus, negative times a positive would make it another negative function, and so I could factor negative out and end up back exactly where I started. Again, this is one of those from algebra that kind of doesn't hold over very well. If you need some extra help, I strongly encourage you to look up even odd functions. There are also some pretty decent examples in our textbook. Okay, let's assume we don't think of this. Let's assume we forget this theorem exists. How do we solve it by hand? Thoughts? Integrating directly?
Yes, just brute force.
Can't. Won't work out.
Oh, dear. Did you just use
Do a substitution of some kind? Yeah. Okay, so if we're going to use substitution of some kind, what's going to be our u for this function? Sine x cosine x? Then its derivative would have to be in the problem. So I have to think to myself, what's the derivative of sine x cosine x? Derivative of sine x cosine x would be sine squared x minus cosine squared x, which is not in the problem anymore. So like that's the most obvious solution. Like it seems like the right one because it's kind of there. There's actually a less obvious one that is actually right and maybe a little easier if I perform some algebra first.
factor out of sine x?
Factoring out of sine x is a good way to do it. What else could I factor out?
Oh.
If I factor out a sine,
And
I think you'll see something interesting happen if I factor out the cosine. Now again, I'm looking to pick a specific u whose derivative is in this problem.
if you were to
Sine.
factor out the sine, wouldn't that be sine squared plus 1, so would this equal cosine? Then you could just
It'd be sine squared minus 1.
minus 1, okay.
Yeah.
Alright.
I like the idea. You're trying to use a trig identity. It doesn't work here though.
Sure.
Very close though. Why, Abby, would I choose sine of x? Yeah, so the derivative of sine, so that would be our du, would be cosine of x dx, which this is in our problem, right? Now if I did that, let's do one piece of time here. The cosine x and the dx would disappear, leaving just du. Everywhere there's a sine, I replace with a u, so instead of sine cubed, I'd have u cubed. Instead of sine, I'd have u. This is much easier to integrate. Much easier to integrate. Okay, well, I can't just change the numbers on the inside and the pieces on the inside. I can also change the bounds, right? That was our theorem from yesterday. So let's plug in negative pi over 2 and positive pi over 2 and see what happens to these two numbers up here. What happens if I plug in negative pi over 2 into sine of x? The unit circle. What happens if I plug in negative pi over 2 into sine of x? I get negative 1. What happens if I plug in positive pi over 2 into sine of x? I get 1. Unit circle's your friend. And don't be ashamed if you do any calculation times, right? If you plan on taking the AP exam, I would suggest taking some time to rememorize the unit circle. It's very helpful for that exam specifically. Because again, there's two parts to it. One that requires a calculator, one that doesn't. And there's sometimes some trick ones on the one that doesn't because they want you to use the unit circle. Okay, now this one, I can now brute force. Okay, so I'm going to integrate this. All right, what is the integral of u cubed? 1/4, u to the 4th, plus the integral of u, 1/2 u squared, evaluated from -1 to +1. Okay? So plug in. I start by plugging in the positive one, so it'll be 1/4 times 1 to the 4th plus 1/2 times 1 squared minus 1/4 -1 to the 4th plus 1/2 -1 squared. They are the same thing. They're both 3/4. So when I subtract them, I get 0. Now, by comparison, if I saw this was an odd function from the very beginning and tested it very quickly, the solution would have been, well, there's my equation. It's odd, therefore it's 0. You don't have to guess what the u is going to be. You avoid a lot of the clutter of this problem. If we thought of 3 different possible u's, I showed one of them working. There is another one that does work, and it's the cosine. It just takes a little bit more work to use. But again, it's doable. Doesn't mean you want to. These theorems can and will simplify some problems. It's just the way it works. But again, that doesn't mean you need them for every problem. You just want to look for specific ones that match that situation. If you find you're struggling to determine a u, maybe from now on start saying, well, maybe it's an even function. Maybe it's an odd function. I don't know. Let's look. Because if you do, then you may just make an easier solution out of that problem. And if it doesn't work, it usually doesn't take much time to check. Testing even and testing odd usually takes no time at all. You can test both at the same time. So, another example. This time with the even function. Let's see. This one is, yep, number 104 and 101. Boom. Let's do it. Number 104. Okay. Number 104 states the integral of -2 to +2 of x times x squared plus 1 cubed dx. Another good indication that this is probably a good way to at least test is if you see the two bounds match. That's usually a good sign that you might try this shortcut. Again, it's not required. It's a good idea to guess that it might work. I'm going to again do this problem assuming I don't see this technique. But then I'll do it again at the end, and we'll see that it's significantly faster. Okay, let's start this problem pretending we don't see it. Okay. All right. What's my u? X squared plus 1. Why would I choose that as my specific u? If I drew this in the problem, what is du?
X, 2x.
2x dx. Now, I have an x dx in the problem. I do not have a 2x dx. How do I fix it?
Uh,
Divide by 2. So I end up with 1/2 du equals x dx. For your information, I like to think of this as a substitution, right? I'm substituting in anywhere I see an x dx for 1/2 du. Okay, let's see what happens over here. Integral. My x dx is replaced with 1/2 du. And I could, because it's a constant, put the 1/2 in front, which I'll probably do in the next step. But you could skip a step here and just go ahead and put it there. Now, that means my x is gone, my dx is gone, all that's left is x squared plus 1 cubed. X squared plus 1 we already said was u. So all I'm left with is u cubed. So again, like I said, I'm going to go ahead and take that 1/2, move it out front, and now I integrate. Before I integrate, let's go ahead and fix our bounds. What happens at -2 and +2? 5?
plug it into U.
Now right here should send up a red flag too.
Yep, let's keep going. Who cares?
What do you know about those two numbers? And if they're the same, what happens to my integral? It will always be 0. Because again, what you're saying is, I'm determining the area between 2 points that are in the same spot. That area's got to be 0. But again, assume we don't see it. Okay? Well, I keep going. I have the 1/2. The integral of u to the third would be 1/4 u to the fourth from 5 to 5. And then from there, plugging in everything kind of just pops out. So 1/4 times 1/2 would make us 1/8 times 5 to the fourth minus 5 to the fourth. And yeah, you get 0. If we had seen from the get-go that this was in fact an odd function, we would have been done a while ago. I did want to show you an even function. I think
What's an even number?
there it is, yeah. I think, ironically, all the evens are the odd number problems. So you know what? Let's do an odd number problem.
No, it didn't work out the other one.
Yes? So maybe I do the wrong odd,
Maybe.
but maybe I do the right odd.
You would know.
Who knows? You don't know how to count by every other odds by now?
No. I
103.
should, like, look at my homework and be like, okay, so we've done that one.
Oh yeah, it's like
I did that one.
103. 1 through 109, every other odd. Integral from -2 to +2 of x squared times x squared plus 1. Yes. This one is an even function. If I plug in a -1, the negative disappears. They have no difference between the two. Now, how am I going to solve this thing?
no.
Try making it 2 to more 0 to a of the function.
So if I recognize it's even, yes, that will be the shortcut I eventually use. Let's assume I don't see that. Let's verify first we can solve it without the shortcut. As always in math, you got to take the long way first. Then you get the supreme joy of being like, the easy way. Yes, thank you for the easy way. How do we solve this?
Distribute the x squared.
I would distribute the x squared and then integrate this function. A lot of people will look at this the first time and be like, let's do a U substitution, and you'll quickly find bad things happen. If you choose like u is equal to x squared plus 1, then you have to work backwards to figure out that x squared is split into x times x, and it's kind of nasty. Let's just distribute. Like, U substitution only works when you want it to work. Don't assume it's the main way to do every integral. We did plenty of problems without U substitution. There'll be plenty more that you will do without U substitution. It's just another tool in the toolbox. So integral, -2 to 2 of x to the fourth plus x squared dx. Alright? Let's integrate. What is the integral of x to the fourth plus x squared? 1/5 x to the 5th. Plus 1/3 x to the 3rd. That's a 4. I hate you. Evaluated from -2 to 2. Okay, so now we plug in. I plug in 2, so I do 1/5 times 2 to the 5th power plus 1/3 times 2 to the 3rd power minus 1/5 times -2 to the 5th power plus 1/3 times -2 to the 3rd power. Okay. 2 to the 5th times 1/5 will be 32 over 5. Plus 8/3. Now, let's fix this set over here. -2 to the 5th. -32 times 1/5. And then the negative sign will turn into a positive 32 over 5. -2 to the 3rd. That's 1/3. Negative of that. So we end up with this rather annoying fraction 64 over 5 plus 16 over 3. I'm not going to bother. Good enough for me. Now, it's a little faster if you see it as an even function because, well, the last piece. Rather than having to do basically the same math twice, only I'm doing it once. So Abby said, we take this function and we integrate twice from 0 to 2 instead of from -2 to 2. It's double the 0 to 2 of the x squared times x squared plus 1. Everything pretty much ends the same, except right here, this piece becomes doubled with a 0 on the bottom. And when you plug in the 0, that piece just kind of goes away. Because again, you're plugging 0 into a function with x in both parts, so it'll disappear. So the math gets you there a little faster, a little easier. Again, it doesn't mean you can't solve it without this. It just means it's easier to solve it without it. So, even odd functions. If you see that it happens to have symmetrical boundaries, this might be one you want to consider doing this technique with. It is not a requirement. There are a few functions where it does benefit you severely to do it this way, because you just end up with a piece that actually fits nicely together. And don't forget your basic integration stuff. The fact that you can take an integral and use algebra to simplify it. The fact that you can take an integral and split it into multiple integrals. The fact that you can take an integral and U substitution now. With again, anything you want to be your U. Something complicated or something simple, you just gotta follow through with it, changing everything to be in that new variable. That is it for this week in terms of new teaching. Homework will be due Friday. 1 through 109, every other odd.
You were doing it on Friday, and you still haven't uploaded it.
I already did.
Oh, you just did?
Yeah, that's why I took forever to start the class. Whoa! What you got?
You said you were going to
What you got? Wait, hold on.
one day.
There seems to be something right here, Abby. It's gone now.
I sat down to do
Probably.
it last night, and it wasn't good.
Like, if you look too close, all these shirts. There's
So it won't be.
glue for woodworking project. This is a piece of metal that burnt my shirt. Let's see. This one with the button tore off because we got it caught on a bridge.
On a what?
We were building a Da Vinci bridge and got caught on a button. And so the thread is a different color than the rest of the threads. These shirts work out. Okay, I'm going to pull up a couple of U substitution problems that are from your homework, and we're going to work through this. What you guys think? U substitution is the main purpose of this section. All of them could use it. Again, I emphasize the word could because, well, there are other techniques you can still use. You are strongly encouraged to use them. So please do not assume that that is the only way or even the best way. Just be open to that idea that it will work. Let's look at one. Oh, there are a couple that say use the graphing utility to solve the integrals. I want to remind you guys about your calculator's functions. If you're integrating by hand using a calculator, The Casios and the TIs all have an integration function pre-programmed into them. Remember, if they're in the wrong form, just make sure to correct that form. So if they're in terms of t, your calculator probably went in terms of x, which is fine. For mine are stationed under the math tab. Towards the bottom, it says fn integral, or finite integral, so number 9. It also, remember, does derivative stuff as well, which is pretty nice. And summation stuff. The Casios do that as well, so take a look at those if you need some. There are a couple of homework questions that specifically state solve using a graphing utility to evaluate the function, and then to graph the region afterwards. So all of that is graphing calculator intensive. Please use what you need to do that. From here, this is number 98. Number 98 says, take the following function, x cubed, square root of 2x plus x, sorry, 2x plus 3 dx. It's a function that is not U substitutionable, but the calculator can do it using summation rules in the background. So those rules we talked about in the last section, or sorry, 2 sections ago, where they did it by hand using a limit process, the calculator does that for every integral you give it. So take a look. The integral it says is from 0 to 2 of x cubed times the square root of 2x plus 3. Now, as you might imagine, dx, you can try to solve this problem by hand, it's not going to work. This is not one that is easily solvable by hand. There's no good substitution problem that will work with this. But the calculator does it just fine. 9.945. Man, I did so good I did it by hand, I did it in my head. You didn't even see me do it. I did it so fast. And you're also welcome to use that to check your work when you're doing homework problems. I give you a solution in the back of the book, as Michael requested from now on. I think it was Michael. And you also have the ability to calculate the calculator. Use that. Make sure you're doing it right. But if you're not, we need to know so we can fix it. Otherwise, it should be everything. Yeah. Oh. There was a question about slope fields. We did those a couple blocks ago, so I want to remind you guys, we use Desmos for a lot of that. I want to pull up my Desmos. I think it's still have it saved. Let's find out. Slope fields? I don't have it saved. That's okay. Desmos can find it again. Desmos can pre-program in slope fields as long as you tell it the function. And there are a couple of problems that specifically say use a slope field to solve. Why did I do that? That was silly. Desmos slope field. So, I thought the first one was not very good. I tried to get it a couple times, it did not work very well. I went to the second link, which already had one prefabricated, and then just kind of modified it to do what I wanted to do. In this case, just make sure you change your function. It says, note that dy dx is equal to this function, and so in your textbook, that function is listed throughout. So make sure you try it. So this one, I would do, this is number 44. It says dy dx equal to x squared times x cubed minus 1 squared. So I do x squared times x cubed minus 1 squared. And then it asks specifically for what's happening at 1, 0. So we go to 1, 0, which is right here. And remember, slope fields, you follow the curvature of the path. So in this case, starting at 1, you can see how the path is tending towards a little bit up. It gets to here and it starts skyrocketing upwards. So it's going to follow that basic field thing. Again, use your resources, use your tools. Do not give up on a problem just because you don't necessarily know how it works. There's plenty of tools out there to help you. Please, please, please use them. That's all you today.